Yeah, I'm Stig Hellebust, and I'm a lecturer at UCC in chemistry, and I'm involved in this project as an investigator to look after the source apportionment. So source apportionment is, well, if we look around here, you've got ship stacks, you've got incinerators, you've got power stations, you've got trucks and cars, and you've got the city over there. And all of this invisible pollution mixes around in the atmosphere. And you can make it visible if you capture it on a filter. If you have a nice white filter and you pump some air through it, you will get a nice black filter, and that is all the mixed pollution from all of these sources. And unfortunately, they don't find nice little organized spots on the filter, so you don't have the pollution from the trucks arriving in one spot and from the ships in another spot. And this means that you have to, after you have collected it, try to unmix that pollution so that you can say, well, you have a certain percent from the buses and the ships, so that you can, well, if you're going to do something about reducing the pollution, you have to know what are the main sources, and that is what source apportionment is about. And we can do this, but we do this with a combination of statistical methods and chemical analysis of the components on that filter, combined with real-time measurements of the pollutants, the particles and the gases in different locations. So it's a very complex environment and a very interesting problem, and we think we can do it. The way we do source apportionment is by chemical analysis of the pollution in the air. So the pollution can be trapped and it can be analyzed, and you can do that analysis in real time with instrumentation, and you can do it by taking the pollution back to the lab and analyzing it. But the important thing is that you know what's in it. The problem is that all these different sources, especially all the combustion sources, and that could be solid fuel burning, or it could be ship engines or incinerators. It's all combustion. They have a lot of similar composition chemically, but they also have some differences. So you need to measure these differences, because you have to use the long-term trends to decipher the patterns. So because they all mix in the air, you get one mixture. They don't separate themselves before you sample them, so you have to separate them afterwards. And I like to liken this process a little bit like it's a bit like getting the milk out of the cappuccino, because it's easy to mix the cappuccino, mix the milk and the coffee. It's very hard to separate them, but we can do that. Well, there are many answers to that, because we're always discovering new markers. But what's important with a chemical marker is that it is specific to a source, and the more specific it is, the better it is. But a lot of markers are specific to maybe a handful of sources, but they are stronger for some than others. So take, for example, an element like potassium, which is a very good marker for biomass burning, solid fuel burning, say wood. But it's not exclusive to wood. You get potassium in emissions from other sources as well. And you have things like vanadium, which is a heavy metal, which is a very good marker for ship emissions, because of the heavy fuel oil that ships burn. It has more vanadium in it than the fuel, say, for road use. But again, it's not completely exclusive, but it's a good marker, and we are always looking for new chemical markers that are specific to certain sources. But if you have a handful of markers that are reasonably specific to some sources and another few markers specific to other sources, you can use that to separate the sources statistically when you have measurements over time. The very best markers are single particles that you can identify from a source, and that is something that is also possible. It's also possible to analyze a single particle of maybe half a micron size and get a chemical analysis of that in real time. With modern instrumentation, this is possible. And then you can actually relate the composition of each individual particle to a, because you have to remember, when you analyze a filter, you get a collection of particles, so you get them all together, and that's when you're relying on good markers. So it's to do with the chemical analysis and relating the composition of the particles back to the composition of the source emissions.